everyone. Thanks for coming. I sent John an email about an hour after this paper came out to tell him I thought it was, quote, super cool. So imagine my delight when I found that he was going to be here already to in fact give a talk at the KSCP on Thursday. And I'm very happy that he has agreed to also tell us today about this really interesting work. I think I had to unshare, so let me go back to this. Is this what? Yes. Is there a way to make it? Is this button make it full screen? What? Oh, perfect. Wonderful. Great. Thanks, John. Whenever you're ready.
Just use the button or
The buttons might be the best way. I don't know. This button, this looks like it turns something off.
yeah.
That's
fine.
We have a stick if you like. Okay. Sorry.
Sure.
I think the keyboard should advance it. I don't know that we have another. Good. Whenever you're ready.
Yeah, cool. Thanks so much for giving me the opportunity to speak. Yeah, I'm really enjoying being in Chicago. Very nice. So what I'll tell you about is some work that I've been doing, trying to understand spaces of theories. And in particular, so I'm going to give some context for why I think this is an interesting problem and how it relates to some interesting aspects of quantum gravity. And then describe how we can use tools like information theory to understand these kind of very universal properties that people have seen in string compactifications. And so my main motivation is really one that's kind of fundamental to theoretical physics, is to characterize the space of physical theory, possible physical theory, and to characterize the relationship. So when I say physical theory, I want you to think of something that depends on a set of parameters, which are called var phi. These var phi are going to be continuous parameters. I'm going to think about them living in var n, or a small n denotes the dimension parameters. I give you a bunch of these parameters, like 1, 4, 8, so on and so forth. And then I think about a theory as being a machine that takes in those things and spits out a bunch of predictions that you can then test. So some examples, some familiar examples are like these parameters could be the temperature and magnetic field of the Ising model, where the Ising model makes statistical predictions about when two-point functions spins and so on and so forth. It could be the Wilson coefficients for some scalar field theory. So I give you a bunch of these coefficients along with a particular type of renormalization scheme, and it spits out a bunch of stuff that I can then compare to an accelerator. More abstract examples are like, I tell you how weighted a coin is, the mass distribution. And that will make predictions about whether it gives you tails or heads. Or I could tell you about the weights of some neural net. These are all types of prediction machines that I'm thinking about. And so what we want to do is we want to understand how do we study these theories and how do we encode the relationships among them? And historically, it's been very, very useful to encode these relations geometrically. So I define some metric on this space, and that metric gives me some sort of thing that I can look at as I vary these parameters and tells me something interesting about that family of theories. And one of the nice things is that these types of metrics shows very naturally in highly symmetric. String compactifications is supersymmetric theory. There are natural notions of the metric on moduli space. There, the parameters of my theory are the devs of fields, or the boundary values of fields. And as I change those, I get a different field theory at each point. It makes a different prediction. And this metric encodes some non-trivial relationship. Similarly, I can have a metric on conformal moduli. I have two marginal operators that take me from one point and deform me along this manifold, this family of theories. And I can define is called the Zamolodchikov metric in terms of the normalization of the 2-point function of the marginal operators. And so what we can use this metric for is as a way of characterizing this entire thing and identify certain exceptional members, some members that are qualitatively different. And the main focus of this talk is to understand the types of singularities that you can have in these metrics. And they fall into 2 classes. They're finite distance singularities, and these are very familiar. So I think about starting a theory at bar phi naught, moving along a particular curve, and then measuring the distance of that curve with that method. And there can be a point here I've labeled it as epsilon equals 0, where the metric blows up. But it blows up in a way that this distance is finite. And it turns out that these finite distance singularities are very familiar. They're where you have quantum critical phenomena. It has the metric. It depends as a function of the correlation length of the theory C. And generically, if I'm deforming away from that critical point with an operator with dimension delta, as the correlation length blows up, this can diverge. It turns out that these are always at finite. So they're typical quantum critical points that go through it. And we know with these types of theories, there's some organizational principle. Mean field theory breaks down here because there are large scale invariant fluctuations. But we know how to repackage our description of that system in a way that allows us to make predictions. And in fact, now we think of these as being kind of the fundamental defining building blocks of the space of quantum field theory, right? Define a critical point, and then you define some deformation of that critical point, and you flow down, and you define a quantum field theory through that. The goal of this talk is about infinite distance singularity. Yeah.
If a theory goes to a gap phase, does it also have like a decouple or something that would also have in finite distance singularity? Or
So I think if it flows to a gap phase, it will not be at infinite. It will not have a finite distance singularity. At least in the cases that I'm familiar with, you really need to have the correlation length blowing up in order to get that finite distance. You also need to be perturbing with a operator whose dimension doesn't make this negative. So there's a bound on the dimension of the operator too. So it's not always the case that a quantum critical point will be at a finite distance singularity. But if you have a finite distance singularity and some assumptions about the locality of your Hamiltonian or your system, then you can argue that this will display a finite distance singularity. So there's been a lot of interest in what are called infinite distance singularities. So you have this metric, and you explore your space of theories, and you find that there are some theories that are at infinite distance. They exist at the boundary of the space. And quite interestingly, if you study ensembles of string compactifications, there's always a very dramatic quantum gravitational behavior that happens there. You seem to universally find a tower of light fields that compresses in mass with respect to the Planck mass as you approach that point. So throughout this talk, I'm always going to be talking about a 1-parameter family of theories that's labeled by epsilon. And I'm going to set that infinite distance singularity at epsilon equals 0. So this is formalized by this thing called the Swampland Distance Conjecture. But the main thing to take away from this is at these infinite distance singularities, there seems to be some universal phenomenon. And so what we wanted to do is we want to understand what is the origin of that universal phenomenon, and if it actually is universal. what are the fundamental features of those infinite distance singularity that are really telling you, that are really demanding that you have this sort of behavior? And why is it happening? So we can do a comparison. We look at finite distance singularities. You know, these singularities are universal in the sense that as I'm going into epsilon equals 0, it behaves some power law that's determined by the dimension of this perturbing operator. Similarly, infinite distance singularities are also universal. It's always just like logarithmic. And there's a coefficient that seems to also display some sort of universality. In finite distance singularity, we have mean field theory breaking down. In at least gravitational theories, the concept of local field theory seems to break down as a new thing. They share very similar.
What's an example of one of the kind of parameters that you're setting to infinity?
Yeah, so in these types of theories, like the classic example is they send the radius of some cycle to infinity. So then these light fields or KK modes could also shrink it to 0, but it could also be like a gauge coupler. Send that to 0. A bunch of light fields. It seems like anytime you have one of these infinite distance points, it's always associated.
Can you say something more about what you mean by local EFT breaking down? I mean, you have infinitely many light fields, so in some sense, definitely, conditionally, it does, but I guess you're going to tell us about the physics of the.
I should say I don't really like this phrasing what happens to a family of theories in terms of a breakdown of a description, because that's not like a positive state. And part of this work was trying to decode what is actually happening at these points and why. Much in the same way, like it's not enough to say that water boils because mean field theory breaks down. Yeah. So again, for finite distance singularities, there's always some useful organizational principle. We know now we leverage the scale invariance or the conformal symmetry, and we use that as a way of organizing our understanding of that theory. At the same time, it seems like every time we approach an infinite distance point, there's always some weakly coupled description that we can rely on. So why is it? There's always some dual thread that we can go to. So can we understand these universal properties? So this is the main question. That's what I want to answer. Why does this metric around these infinite distance points look like this? Why do they have universal properties? And what's the organizational principle? Why do they have to behave so differently in quantum gravity? And then, as a consequence, when and why should this conjectural statement be true? Is it actually always true? So the tool I'm going to be using, this is the main idea of the talk. I'm just going to tell you what I'm going to talk about for the entire time. The tool that I'll use is this thing called the information method. This is a very fundamental object that I can define on any family of theory that is ambivalent of the description set. This characterizes a family of theories and defines a notion of a metric and a geometry for any family of theories that doesn't depend on a particular computation. It tells you about the kind of inherent differences between different theories. And it turns out, if I study this in a family of supersymmetric theory, it reduces to the moduli space metric, proportional to the moduli space metric. Similarly, if I study in a family of conformal field theories, it reduces the metric on conformal moduli.
Is this like the KN divergence of the downstream?
Yeah. So it's the one way of thinking about the classical information. Thank you. So this gives a way of defining a notion of metric that is inherent to a family of theories and doesn't rely on any sort of symmetry. just the right thing to define. And it reduces to the well-known right things to define in families that have been studied. And what you can do is you can argue that anytime this thing has an infinite distance singularity, unitarity is the thing that forces it to behave logarithmically. The only way that you can get an infinite distance singularity is if this behaves logarithmically, and as a consequence, some expectation value of some degrees of freedom, not necessarily like the ones that you started with, have to begin to factorize. And factorize, and what I mean by factorize is that I remove all statistical ambiguity.
What sort of assumptions do you have to make about, like, does it have to be a relativistic field theory or something for the information metric to exist, or
No,
can I start with something that is?
I can define the information metric for a coin. I can define the information metric for a ball. I'm not sure what other sorts of
Yeah.
systems.
But
Um,
I was wondering if you had a RG equal to a non-unitary CFT, you would have a worse divergence, or?
So I don't understand what happens when you disobey unitarity. I'm really thinking about, I have a machine called quantum gravity or string theory. It gives me a way of accessing information about a wide class, a continuous family of theories, which stay unitary as I move along that space. And then under those assumptions, what do these infinite distance singularities mean? I thought about these, what happens if you start relaxing unitarity, but then the tools don't even make sense. This is really a thing that relies on saying, I have something that makes probabilistic prediction or quantum prediction. It's a thing that like is inherently tied to the fact that I'm studying probability distribution in a way that I'll describe.
So you could have a non-unitary field theory for making statistical.
Well, I would say that if it's not unitary, if it's not making unitary predictions, I don't have like a concept of a probabilistic system that.
It's like non-unitary, but.
So yeah, I should say there has to be a concept of non-unitary, which isn't so bad.
Yeah.
I think that's, but yeah, I want unitary. Let me use.
This factorization is always for local operators?
No. So what I can say is that there's some degrees of freedom that factorize. It could be that those degrees of freedom live on like the boundary, in which case you have a lower dimensional description, which is factorizing, or they live in a different dimension. So the concept of locality is a little tough. So then the question is, like, why do these infinite distance points obey so dramatically in quantum gravity? And it has to do with the simple fact that gravity couples universally to stress energy. It always provides some irreducible type of statistical ambiguity to your observables. Gravity, in some sense, provides a lower bound on how decoupled things will be, lower bound on the forces. So anytime I try and factorize something, there are always going to be graviton corrections just from the fact that these things will source stress energy, and gravity will couple to that stress energy and communicate with these. So I can only consistently realize an infinite distance limit or a factorization limit in these theories if I do something that decouples gravity. So one way of decoupling gravity is to send the Planck mass to infinity. And anytime I send the Planck mass to infinity, that always requires that I add a bunch of states. Either those states are heavy, in which case they're black holes. And the Bekenstein-Hawking bound tells me that the number of those diverge with the Planck length as the Planck length goes to 0.
Are you united from parameter, or you also divide?
Yeah,
Will be part of the epsilon.
yeah, exactly. Yeah. So I'm imagining I have some family of theories that is parameterized. And then the Planck length can change. How does that sound to you? Does it change? Okay. So that was the main idea. Kind of if you want, you can just decouple and like go into your mind space. But what I'll do now is kind of explain more aspects of this. I'll introduce this information metric, tell you what it's quantifying and what the operational definition of it is. Then I'll describe how these logarithmic singularities emerge out of these probabilities, out of this information. In some sense, the logarithmic singularity you can understand is anytime I want to make a probability distribution taller, so the area under it or the volume under it has to be conserved, has to be 1, it has to shrink like this. So as I send epsilon to 0 and make this very, very small, it has to be a shrinking of the weight under that curve, of the width of that curve. And this gives me this kind of emergent scaling symmetry of the distribution, which gives me this logarithmic singularity. So the reason why these infinite distance singularities always have this universal form, this motion. And as you can see, if that's happening, then there's a complete collapse of statistical uncertainty. I get localized to a certain event. And so I know that there's some observables that factor. And then finally, I'll talk about how this story plays into quantum gravity. Okay. So I think the best way of thinking about the information metric is in the context of classical probability distributions. So I remove quantum mechanics, I just consider statistical field theories. I give you a family of probability distributions in terms of this phi, the fields, the scalar field, and as a function of parameters modified. Harkening back to this field theory is living on top. And so I have some random variable, they make predictions for some random variable var phi, which I'm assuming is continuous. It has dimension n. And then there's a bunch of parameters which define this thing. And there's a result in classical information theory by Chenkov, because there's only one way up to an overall constant to define a metric on the space that treats each of these points as actual probability. They behave nicely under singular probability. And as you mentioned, this is the infinitesimal form of the KL rendering. This is one way of computing this information. There are about a million different ways. Because it's unique, you define a good notion of distance among probability distributions, and it always reduces this. And what we can understand this thing as doing is as assigning a distance between different theories based on how distinguishable they are, using the best possible measurements. Okay, so the game that I would like to play is I want to design an optimal test, the best possible test that I can do that distinguishes theories from the theory of what I've labeled for. Okay. So the game I play is I hand you m samples. And I want to find the best possible test that tells me, given those samples, whether or not those samples are from the distribution there. Okay. And what Sanov's theorem says is that the optimal test will be able to distinguish this theory from theories outside, and eventually defined by this information probability 1 minus. So as I give you more and more measurements, this ellipsoid shrinks, m goes to infinity, And it becomes easier and easier to distinguish theories at different parameters. Okay. So what the information metric does, the way you derive this is you make statements about the KL divergence, and this is the infinitesimal version of the KL divergence. It tells you, given the best possible sampling, combination of variables that I can look at, how distinguishable two different theories are. And crucially, you can see that this object is invariant under arbitrary redefinitions of my random variable. Okay? That's what drives its ability to make statements about the best possible presentation, the optimal presentation. And that's really, I think, the main power of using these information theoretic techniques. It doesn't rely on my description, it relies on the best possible description. Let me illustrate this in a very helpful example. Just some Gaussians. Gaussian in a random variable x with variance sigma and mean mu. As I change sigma, broaden or unbroaden the distribution. As I change mu, I shift it around. And funnily enough, the information metric associated with this class of distributions is just Euclidean ADS. And as you can see, if I ignore this part, sigma, the variance, sets the units in some sense for the distribution. So if I make sigma very small, it's relatively easy to distinguish between them. Similarly, if I send sigma to 0, make it very small, I get a delta function. And a single measurement of not mu can immediately rule out the distribution. So it's infinitely distinguishable. So I talked about the classical information metric defined on classical probability distributions. You can define the quantum information metric as kind of a natural extension of that classical information metric to quantum states. So I give you a family of quantum states in a Hilbert space. It doesn't have to be vacuum from states, it's just a family of states. And I can immediately define a notion of metric or distance on that space via this object. And the key thing is that if I pick a basis to represent the state in, this defines a probability distribution for those variables. And in that probability distribution, this quantum information metric reduces to the classical information metric, plus some phase information.
I mean, one thing that one might worry about is the fact that now you have these very like infinite dimensional spaces, and you might not even have a basis, let alone things. Even if you have a metric basis, things must still break down.
Yeah, so I'm always going to be using some sort of regulator that allows me to compute this thing. It turns out that, at least for field theories, this is just infinite. In the same way, the energy of an infinite volume is infinite because it's an extensive quantity. This thing is an extensive quantity in the number of degrees of freedom. You can define an intensive version which strips off that stuff and gives you a well-defined notion of distance. And it turns out that's the thing that's proportional to the moduli space metric and the analytic metric. And the thing that I will study. So another thing I want to point out is that if I can choose a basis in which this stuff is 0, or this phase is constant, then I just get a classical information metric for that family. And in some sense, I think the way to think about this stuff is that while the classical information metric tells you what is it characterizes a family of theories based on best case distinguishability, choosing the best possible combinations of phi to look at. the quantum information metric is including the fact that there are other bases that I can choose. I can choose like momentum basis rather than phi basis. There are other types of bases that I can choose, and the quantum information metric is sensitive to also the best case possible basis. I slept a little bit. So here, I'm only talking about state. Maybe on the next slide. Yeah. I can define a metric on a family of theories by how well I can distinguish between them using their vacuum expectation values. Okay. So I'm going to define a notion of distance between different means based on how easy it is to distinguish them from their vevs, their 2-point functions, their all of the sorts of correlators that we look at. And as I mentioned before, this information metric is going to be extensive in the number of degrees of freedom. And so I need to peel that factor off and look at the proportionality, how that blows up as I change the number of degrees. So if I wanted to, there are so many different ways to compute it. Maybe one of the easiest ways, the most familiar, is if I define a family of theories by some deformation of some Euclidean action. I deform a Euclidean action, I move along this space by deforming by some operator with dimension delta. And then the information metric associated with that can just be read off from the 2-point. As you can see, if I define the Zamolodchikov metric as something that knows about the structure of the 2-point, the normalization of the 2-point function, once you get rid of all of these stupid lambdas and L's and stuff, you just get this strict proportionality. So again, we can now go back to our Gaussian example. For just this, the harmonic oscillator, I can define this information metric. It's just a Gaussian, again, with no mean. And I see that again, it has this logarithmic type singularity. As I send omega to 0, or I send omega to infinity. Right? As I send omega to 0, I know that I'm completely unfixing the particle from the minimum. It can be anything. So the ground state is just spread out p equals 0. And I know that if I measure the momentum of that particle, I can immediately distinguish it, because if I measure any non-zero p, I know I'm not at that state. I'm not in that theory. Similarly, if I send omega to infinity, I fix the particle in place. And if I measure the particle anywhere that's not at x equals 0, I immediately know I'm not at omega equals infinity. Okay? So that's really the thing, is this information metric is able to know about the best possible measurements.
I have a question, which is, if I was doing purple, is there a version of this called a density matrix instead of just a state?
Yeah, so there are extensions of this information metric to mixed states as well. Here I'm only going to consider yours. There's no classical ambiguity about what the state is. I'm not sure how much of the story translates to mixed state, but I think a lot. Okay. So as a recap, what I want to do is I want to understand what these infinite distance singularities are in the metric on moduli spaces and the Zamolodchikov metric by translating it into properties about this information metric. And I can define the information metric on vacuum states, the vacuum state of the family of theories. And as long as I restrict appropriately, I get these things. It gives me another way of understanding things that I already know about these different metrics in an information theoretic context that is ambivalent about my description of the theory. And it tells me optimal things about these different theories, how distinguishable they are using the best possible measurements in the best possible basis. And from our Gaussian case and our harmonic oscillator case, we saw that there's this, we had these infinite distance singularities already appearing in like the simplest theories in the world. And so what we want to understand is, what does the harmonic oscillator have in common with the F theory that's compactified on some elliptically fibered fourfold that degenerates? What is it about these infinite distance points that are shared between these two extremely different systems? So what I want to do right now is just study classical probability distributions, a one parameter family of classical probability distributions in phi. Right now, I'll just assume it has a single dimension, and send epsilon to 0 and ask, what sort of behavior can I have this distribution execute in order to get an infinite? So I can have any arbitrary shape here, but just doing a scaling analysis, if I send epsilon to 0, if this family of probability distributions approaches an arbitrary fixed distribution, like this shape that I've drawn, then I can never have an infinite distance. And we understand that from an information theoretic point of view. This curve in blue is not so different from this curve in red. And if I do some samples, it's pretty hard to distinguish whether or not they came from blue or this red here, or even this red here. If I give you like 4 samples, it's pretty tough. And what we see is that you can have finite distance singularities if the dependence on this parameter is fractional. I can get a finite distance singularity, but because epsilon has to be, this power of epsilon has to be positive, because this has to be a well-defined family of probability distributions. It can never be negative. It always has to have unit weight. I can never get this infinite distance singularity. Okay. So then a good question is, like, how do I get it? Like, this was a fairly general parameterization of this. But it did assume that the amplitude, like in terms of a pointwise expansion in epsilon, it did assume that the amplitude of this was not divergent. So if I allow the amplitude of that thing to diverge, I have to have, there has to be a piece which is shrinking in width. Okay? So there has to be some choice of variables that I can choose where the amplitude is getting driven up, the width is shrinking. And because of this scaling symmetry that has to emerge, because of unitarity, because these are probability distributions, I have to get something that goes like one of our examples. Here I'm making I'm assuming that expectation values remain finite as epsilon goes to 0. And if I relax that assumption, I can get other powers. But what is not, what won't change is the fact that anytime I have one of these infinite distance singularities, I'll always have this factorization. I'll always have that my probability distribution is in some sense collapsing to a point. Okay. So here I've generalized to n degrees of freedom that are factorizing. Some other degrees of freedom don't necessarily have to factor. And in that case, the metric is proportional to the sum coefficient times the number of degrees of freedom that are factorizing times this logarithmic structure. Okay. And so the point I want to make, and the point that I want you to take away from this, is that infinite distance is really associated to a factorization, a point where statistical ambiguity vanishes. And you can go through and you can see this explicitly in a number of examples that very, very wide. And there's always this set of degrees of freedom that are factorized. Okay. So again, in this Gaussian case, we have this infinite distance singularity as sigma goes to 0 or sigma goes to infinity, because these correlation functions of this observable are factored. They collapse to around the one more minute today. Okay, good. So then you can ask why. Yeah, a harmonic oscillator has an infinite distance point. F theory has some infinite distance points, but the nature of that infinite distance point in F theory is very, different. If I have an infinite distance point, just quantum field theory, they don't necessarily have this infinite power of fields. But if I look at quantum gravity, it seems like I always have to have this power of length. And so why are those appearing? What is it about gravity which is forcing me to have this? Why would factorization require this behavior? And as I said before, intuitively, gravity is going to couple universally to stress energy. So it's always going to present an obstruction to factorization. And I need to do something to the theory which disrupts this universal attraction that gravity supplies. And so in order to consistently realize one of these factorization limits, I need to turn off gravity. And this can be seen pretty easily just using logarithm. So I'm going to consider some scalar primary with some scaling dimension delta, and I'm going to make sure that it behaves holographically like a gravitational theory. So it's coupled to some local stress energy tensor P with a normalization of the stress energy set by this coefficient CP. Okay. And we know just from the basic holographic dictionary that this CT, at least when A equals C and I'm at very large CT, that this is going to tell me about the ratio of the ADS length to the Planck. And so I can think about, I have my ADS, there's like LADS, and I start putting operators boundary and asking what their correlation. What do I have to do in order to get those correlation functions to factor? So if I have a 4-point function, I want to approach a factorization limit, this is what the factorization. Have a bunch of 2-point functions. And the key point is that at least when I don't have a legitimately free field, and I'm above the unitarity bound for this operator, this is a generalized free field, and it can't be consistently coupled to a local stress energy. There's always a contribution that is dictated by conformal invariance of stress energy exchange or graviton exchange that just can't be canceled. And so in order to decouple these two things and approach this form, I have to drive CP to infinity. Okay. You can read this as this is the mass of the field, and this is the Planck mass. It's really graviton exchange, which is providing this obstruction to factorization. And so in order to approach a factorization limit and actually get these correlators to factorize, turn off that stress energy exchange, and you descend the Planck mass to infinity. And at least in CFT, the CT is measuring the number of degrees of freedom in some sense of that theory. And so if I want to send CT to infinity, I have to send the number of degrees of freedom. And I can do that in two different ways. I can do that in a way where all of these states stay above the Planck mass. I make gravity strongly coupled above the Planck scale. And the dual is essentially Einstein gravity, plus a bunch of black hole states whose number diverges as the Planck length goes to 0 or the Planck mass goes to infinity. Or gravity can be strongly coupled at a scale that's much lower than the Planck. I add a bunch of states that don't diverge in mass with the Planck mass, but stay relatively. So there are two options. And if I assume that I'm approaching a factorization limit, and the states that are driving the Planck mass to infinity are not diverging along with the Planck mass, then immediately you can derive this Swampland distance like behavior. So you say that I'm approaching a factorization limit. So in any parameter, if I approach a factorization limit, the Planck mass has to diverge. I can use that Planck mass as a parameter that parameterizes the family of theories. And because this logarithmic singularity is a universal feature of those infinite distance singularities or those factorization limits, I have to have this sort of thing. So as a function of the distance that I define, the distance that reduces to the Zamolodchikov distance, or the distance on moduli space that we normally talk about, the Planck mass has to diverge with some power, some coefficient here, or whatever, exponentially in that. And as long as these aren't diverging along with the Planck mass, they're going to compress in mass exponentially. That's really it follows from unitarity and this consistency of a factorization in a quantum gravitation. And it's pretty natural for this to apply in geometric string compactification. And if I want to send the Planck mass to infinity of some family of theories, I need to blow up the volume of some internal manifold. That's always going to be associated with some like KK modes. But from the context of CFT, this isn't so weird, right? I know that large N factorization exists, trunk coupling exists, that can ensure that there's some large gap that persists as I send the number of degrees of freedom to infinity. So it's pretty natural to see this sort of behavior in the layer posts of supersymmetric string compactification, a function of how they're structured. It seems like you can get these factorization limits without the light tower of states by another very respected mechanism. Sure, some large gap. So I'm going to conclude. This was really the goal, was to understand these universal features of these infinite distance points, why they have these logarithmic singularities, why they're associated with this light tower state, that tower states will become exponentially light with respect to the Planck mass as you approach the distance limit. And in fact, why a weakly coupled dual description always exists, using these information theoretic tools. You make statements about why there's always some weakly coupled dual description, because the information metric is talking about the best possible things that you could look at. And so as I'm approaching an infinite distance point, in any description of the theory that I use to calculate that metric, I know that there's going to be some dual frame that I can find that makes the physics relatively simple. So the point of this is that you can use this information metric as a way of understanding the metric on moduli space and the metric on the Zamolodchikov, these very natural notions of metric that descend from the symmetry structure of the theory. And they're telling you about what the information metric is doing, and the information metric is telling you about what they're doing. They share the same singularity structure. And the nice thing about the information metric is it translates statements about the singularity structure into statements about the the fundamental distinguishability of theory, how different they're becoming. And because these are unitary theories, the way I can get an infinite distance limit, the way I get an infinite distance singularity is by having factorization, complete collapse of the probability distribution of the theory of the state on some finite set of observables. And I can then immediately distinguish that theory or that state from others around. And then you can understand why we see this universal behavior of gravity around these infinite distance points as a consequence of gravity just not liking factorization. It always couples universally. And so in order to decouple it, you need an infinite number of degrees of freedom. And that's where this like comes. So that's the. Know if you have any questions.
Thank you, John. Very cool. Do we have further questions for John? I want to very vaguely return to my question from before. Give me a lot to think about this. Very good. The same question that I asked before. So, indeed, you get gravity decouples, you get infinite number of like states. Can you say anything about or the physics of what that does to your having some observables factorize is not something I have a intuitive notion of
Yeah,
You're saying
I
one of
mean,
those directions.
so the reason I phrase it in terms of factorization and which feels a lot more familiar, is that factorization applies to a large variety of things. So one way of thinking about factorization is that the theory is becoming classical. Things are classicalizing, and instead of having to describe the predictions of that theory using some set of moments or some probability distribution, you just have to give you a single number. Much in the same way in a quantum theory, I have to specify some wave function for a particle as a property, but in a classical theory, all I have to do is tell you a single trajectory.
There's only some subset of the observable, right?
So you can think about, because the information vector knows about the best case distinguishability, observables that are factorizing are going to be the things that your optimal tests are going to look at. So those factorizing degrees of freedom are driving that distinguishability and generating.
I'm assuming that you are not claiming that this is necessary.
Yeah.
So what's the main following?
So I think, I mean, yeah. So there's, yeah. So in this, the types of theories that I considered were, I mean, you have a family of theories that are making predictions for an infinite set of observables. And one of the things that I was really assuming is that as I approach an infinite distance point, most of those infinite degrees of freedom are behaving kind of the same. So they're in some sense assuming translation. That there was not a very dramatic scale. And so that's one thing that I'm confused about and would like to understand is. Sorry? No, I don't think so. So I think roughly what that does is all that does is affect this coefficient here, but I can't really say that I approve. What I want to do is give like find the story based on these scaling arguments that explains why you have this universal. I checked it in as many examples as I can, and it works. And I think one of the things that would be very interesting is, actually exhibit one of these counterexamples to this sort of distance behavior using just holography. I think that's the thing, is I wanted to find a way of getting around the lamppost of supersymmetric string compactification and make a statement that only relies on very general properties about quantum gravity. And from this, I'm pretty satisfied. And I would be extremely interested to find weak points. I think because there's a singularity there, it's kind of magic. You just go close to the singularity and let's drive on it. I think so. So yeah, I should say that this logarithmic singularity is only universal if I'm approaching some fixed set of observations. That was, if I relax that assumption, then the singularity can be more dramatic, but I still get this factorization. And yeah, so I think there's.
Could you say something about how the metric behaves when like the manifold structure breaks down? Because the modular space is not like a quantified manifold to have points at each generation.
In the sense that the metric follows up, or
like I was thinking of like T-duality points. Does the metric how is the growth?
Yeah. So here I'm assuming that I'm not modding out by things that are invariant, so things that are dual. So like if I have P-duality, I have my radius, and there's the self-dual point, and then this set of theories and this set of theories. Right? Here I am assuming that the theories vary smoothly as I move along that space. So there is that wonderful singularity there, which I assume is just working with the double complement. It's not a completely parameter. It could be some problem.
So you're not worried about it because you're infinite at infinite distance. None of this. Like the infinite distance point is not like.
Let me put it this way: if I'm dealing with this self-dual point, I'm only approaching it from one direction. And I never really said that. I only asked. Approach.
But you also see, if I just computed the Samological metric or the frequency count, and of course the optical point, I would also see this logarithmic level.
I don't think it would be this self-dual point.
Yeah, I guess it's not enough distance.
Only the point.
One of the ways that people argue for no localities when they look at the entropy. So like for CFTs, you get the Faraday spectrum, like D minus 1 over D. For gravity, you have like Hawking spectrum D squared. And it seems like your finite distance singularities would correspond to CFTs, and this infinite distance to something more general. Can you look at the entropy and get this kind of results? Like when you study how the entropy varies as you change epsilon, when you go to a finite distance singularity, you get like Hawking spectrum. When you go to infinite distance, you get like D squared, something like that.
Yeah, I think the thing that I'm so you're looking at the entropy of what type of entropy? Like a trace out some subsystem.
Yeah.
So there, since I'm tracing out I'm picking some particularly spatial observable to look at, that's going to inherit a lot of properties about the question I'm asking. Right here, because I'm there, I'm a little like hesitant because it's building in a lot of stuff. I think really the power behind it, like the problem with information theory is it's kind of easy to go in loops and not see the killer app of it. Killer app is really being able to quantify these things in a way that doesn't depend on the question that I'm asking, the optimal. So I'm not sure how to approach or understand that sort of normal power.
For example, Shannon, given that it's also something.
Yeah, so in some sense, this information metric is, so the Shannon entropy is great for the street distribution. The parent of it is really the KL divergence. And this is kind of telling you, I mean, it's kind of telling you about, it's really the infinitesimal KL divergence. There's a bunch of higher order terms that this misses out on, and you kind of have to, that to build in a lot of differences. But it does.
So this information metric has the same amount, same sort of data.
So I think the problem is that it's infinite. The problem and the feature of it is that it's infinitesimal in a sense. So I can have, like, one of the curious things is if I look at the theory of R and the theory of 1 over R, they're dual to 1. The information metric tells me what happens as I measure the distinguishability of all the theories between them. So it can't tell me that these are actually super people. The KL divergence would say that these are actually the same theory because we can. And so it does contain more information, but it also loses some things because there has to be a comparison between two different theories. Whereas this is really giving me like an intrinsic characterization of the theory.
Great, let's thank John again.
What do you define just like the Von Neumann entropy for the related distributions?
So yeah, when you say that,